The project was funded by NSF. And all experimental work was carried out at Dr. Spontak's and Dr. Ghosh's lab. It was a good collaboration, and it meant a lot to me. That's why we have developed kind of e-textiles, and that's our starting point. So I want to start with the e-textiles. The ones who are not very familiar with the e-textiles, they are basically technical textiles and offer aesthetic appearance like as conventional textiles with electronic capability, and that makes them special. You can see some textiles here. On the right corner, it is counted as one of the first electronic textiles developed at GATEC, and it is called wearable motherboard. And after this study, the area started to lots of researchers started to focus on electronic textiles. And for example, this is a messenger dog used for this. This cloth is especially designed for the dogs, and it is used for finding the people who were after earthquake. Some of them, need to be found under the buildings. And this is a mood dress developed by Philips. Depending on the heart rate or body temperature, it changes the color. So, and this is a kind of smart coat. It has some heaters, special heat regulators, MP3 players and headphones and mobile phones, and even there are some applications which are invisible code. We know all these things. E-textiles can be classified according to many criteria, but according to their function, applications, materials, and so on. But the basic classification can be given as here: electronic integrated textiles and textile-based electronics. There is a kind of boundary between these two. The first studies started with the electronic integrated textiles. In this case, they just attach the electronic onto the textile. So textile is just the carrier. But in the other, so this is a kind of heavy, bulky, hard, and these structures have many problems. In order to overcome all these problems, textile-based electronics are developing day by day, especially in the last 20 years. So in this case, textile-based electronics are materials with electronic functions embedded in them. So our aim is recent studies focus on these things. So since textiles are ideal platforms, substrate, carriers for electronics, so they can be used for many applications, including communication, actuators, energy harvesting, and sensing. So the most important ones, one of the most important ones are sensors. Basically, sensor is a device that receives a stimulus and responds with an electrical signal. That means we are controlling the system. So we are learning about the system. We use sensors to determine the temperature, pressure, strain, force, flow, and so many things can be controlled by using the sensors. Not only for control systems, but also they can be used for adaptive systems. So in order to be, the textiles, smart textiles, very smart textiles and adaptive textiles. The trend is going to adaptive textiles. That means making smart, very smart textiles that can easily adapt the environment. And in order to do this, we need sensors in any way. So and clothing provides best platform in various forms and structures, because textile is a very old industry from the beginning of the human being, and so we really know how to make textiles, how to give form, how to fabricate the different structures with different properties. So it is very tunable. Since textiles are very tunable, textile-based sensors are also tunable. So they basically provide an interface between user and electronic system, and they can easily convert, depending on the mechanism, they can convert any type of variable into a meaningful electrical signal. So we are basically classifying based on their sensing mechanism, and capacitive sensing, inductive sensing, piezoelectric sensing, chemical sensing, optical sensing, and piezoresistive sensing. I'm just going to cover all these things very quickly to come to my topic, because I think I need to explain a little bit. Capacitive sensors are basically capacitors. So we have two electrodes and we have a dielectric material between them. Any change in the area, length, or dielectric constant of the material will lead to change in capacitance, so we can monitor the other variable. So how we build textile-based capacitive sensors? The same thing. So we need to have two electrodes and one dielectric material, and this dielectric material can be in the form of a spacer fabric or form or any other thing, like in the form of film or other things, depending on the application that we are interested in. For the pressure sensors, generally they are using bulk structures. So these electrodes and this dielectric material can be fabricated by weaving, knitting, embroidery, or printing. All textile fabrication methods can be used easily. And they can be used for pressure monitoring, health monitoring in the form of belts for belly or chest region, touch and proximity, and for motion detection. The other group is the inductive sensors, and inductive sensors work by emitting electromagnetic field, and there's an oscillator here, and it helps to generate electromagnetic field. And any kind of metallic material will affect the amplitude of this field. So these sensors inductive sensors are commonly used in industry for the detection of metals, but in textile sensor part, they are not very common, because it is kind of it is a little bit harder to fabricate these coils in a standard way by textile fabrication. So it is the fabrication is a little bit problematic and a little bit expensive. Again, they can be done and used for health monitoring and strain or displacement monitoring. And the other group is the piezoelectric sensors, and piezoelectric sensors are generally used for determination of the pressure or any kind of deformation. So in this case, we are using piezoelectric materials, and random orientation of polar domains can be seen here by the application of a voltage. The change in dimensions will be monitored, either as seen from the other side. If we apply pressure, then voltage generation can occur. So by monitoring these two variables, we can have an idea about if this is going to be a pressure sensor or force sensor. We can monitor the force as a function of deformation. So they are also used in automotives easily, and the piezoelectric material can be in the form of film, fabric, lamination, coating, or electrospinning also can be used. PVDF is one of the common polymer materials used for the piezoelectric sensors. And for pressure monitoring, health monitoring, and motion detection are the common areas for this. And for the optical sensors, the thing is the properties of the light beam. So change in intensity, phase, or polarization or wavelength can be used to determine the other variable or other stimulus in the environment. So here we are using optical fibers. So optical fibers can be incorporated into the fabric structure by weaving, embroidery, or stitching. And this is also the optical fiber. It can be a polymer optical fiber or glass-based optical fiber. They both have advantages and disadvantages, and can be used for strain, bending, pressure, or health monitoring. There are many studies about this. And the other one is the chemical sensors. Chemical sensors have sensing layer and a transducer. So the most important thing here is any material specific to the sample should be on the textile. So we can use pH sensitive dyes or hydrogels, or any kind of specific material can be applied on the textile, or can be incorporated into the textile by printing, coating, lamination, or even doing spinning. This all can be done. So this is a, for example, textile-based chemical sensor for sweat analysis. And the other and the most common one is, and also the one that I'm going to talk about, is the piezoresistive sensors. Piezoresistive sensors are work according to piezo resistance. That means any change in electrical resistance due to the applied strain or deformation. If we deform the sample, then we can monitor the strain or any kind of compression deformation level, by monitoring the resistance. And since this is directly related with the both electrical and mechanical properties of the system, we also call them electromechanical sensors. So this is a kind of knee patch used for the people who are doing a lot of sports. So again, we need to use a piezoresistive material, and we can attach or incorporate into the structure by weaving, knitting, embroidery, printing, coating, lamination, 3D printing, or even electro spraying, electro spinning. All these techniques can be used. And also, like the other ones, for pressure, strain, health, and posture monitoring, piezoresistive textile-based sensors are used. Now, if we come to our research part, I would like to talk about the design of a textile-based sensor. Now, there are a couple of things if we want to design a textile-based sensor. These can be given as, the first thing is, of course, any kind of design definition of the problem. Okay, what is our problem? We want to measure something. We want to control any kind of system. So, okay, we need to determine the application, function, form of the sensor, mechanism of sensing. As I explained before, there are various mechanisms, and depending on the mechanism of the sensing, there are going to be some restrictions that in our design space. So, and also there are going to be some limits. So we need to consider also some standards. Yes, there are not international standards about textile-based sensors now, because it is in the development area, but in the coming years, I'm sure there are going to be many standards on the area of, especially for wearable electronics. And also we need to determine the materials and the production method, which is very important also, and of course cost, because there are really good and fascinating electronic textiles on the market, but they're very expensive, and most of the people cannot afford it. And the other one is kind of coming recent years, even a couple of papers I saw last year, sustainability. So design for sustainability and design for recycling. So I have been also working about this kind of project for 2 years. Hopefully in coming 5 or 6 months, it will be ready for publication. I mean, sustainable sensors. It is going to be sustainable electronics and sustainable text sensors especially. So let's look for our case. Determination of the problem, we want to measure the strain level. Okay, so application is going to be the strain sensor. So what is the function going to be? So to determine the deformation ratio as a function of resistance. Okay, what kind of form we want? We want textile sensor. Okay, but what kind of we want? Again, it is going to be on a pant or on a sweat or on a knee. So we also need to decide on this. Or we need to put this sensor on a kind of flexible fabric or rigid fabric, And mechanism of sensing, my professors already decided on this before I start the project, and they decided that they wanted to work about piezoresistive strain sensors. Based on these 4 important criteria, there are going to be some restrictions in our design space. So these are going to be, first of all, if you want to make a piezoresistive sensor, then it needs to be conductive. If you want a textile sensor, then it should be kind of printable or flexible and lightweight and comfortable. And also, the most important thing is, if we are making a textile-based sensor, it should be wearable and durable, and of course, the processing should be easier. The limits of the design comes from basically from the materials that we are using. Since we want to make a wearable and sensor, so it's going to be the restrictions and limits are going to be from the textile, its structure, textile structure. So standards, the first and easy thing and straightforward thing is that should be harmless to the human health and environment as much as possible. And also, if there are some regulations, the system should be okay with the regulations. And cost should be cheap, at least affordable. And materials, based on all these requirements, the project was, for the project, PVC was decided to be used because it is strong, lightweight, durable, and it is one of the most used polymers like PE, PP, PVC, PET, and polyamide. So it is affordable. You can find it everywhere. And there are a couple of companies who produce different grades of PVC. So Solvay is the one that we got our polymers from there. And as a filler, we need to make the structure conductive. So that's why we choose a filler that can give us low percolation thresholds. So recently, we always think about graphene and carbon nanotubes, but they're expensive. Our aim is to make something as cheap as possible, and because as a result, I'm going to tell you that this is one of the cheapest sensors in the in the research, in the literature. Hopefully, maybe in the market coming years. And also for the production method, printing and coating were determined. So before making any kind of textile sensor, we really need to consider all these steps. So in the next step. Fabrication and characterization of piezoresistive printing layer is also critical because, to be able to understand what is going on the textile sensor, we really need to know its behavior in the form of a composite and in the form of a film, because all the morphological, mechanical, and electrical properties directly going to affect the fabric-based, textile-based sensors, because we are going to print or coat on the fabric, so they are going to behave together. So to be able to understand the thing, we need to evaluate the fabric by itself and also the coated layer itself. This graph shows that, in fact, we worked with 3 different molecular weights of PVC, but I'm just giving just one of it here, the one that gives us both good mechanical and electrical properties. We compensate, and we decided on the best one. And here, this is for the ones who are familiar with the conductive polymer composites, this is a classical percolation graph. So it shows the transition from insulating region to percolation region, and even if we go further, we can go to saturation region. So these all these 4 compositions, different Plastisol compositions, showed different percolation behavior. Higher in all cases, if we increase the amount of the carbon nanofibers, the conductivity increased, resistivity, volume resistivity decreased. So higher DOS. Now I am talking about the different Plastisol. Different plastisols we have prepared based on the amount of the plasticizer, deoxysilicate, and PVC. So this is the highest amount of plasticizer in the structure. So when I was making the films, it was very clear that if we increase the amount of the plasticizer, the surface is kind of shiny. So you can feel the oily texture. So, and because of that, this oily and this insulating property led to higher percolation threshold for the samples. And also another interesting thing that Dr. Spontak told me to do, and he came to lab and helped me for taking this SEM field emission SEM images. We had some problems at high accelerating voltages, so he made these measurements at low voltage. So for the ones, especially for the plasticized PVC, working at high voltages is not good because of low TG sample can melt. So, and from these images, we saw that the filler dispersion is good, and there's no dominant filler orientation, and filler matrix interface looks good. So, after this, we also measured the mechanical properties, but since we don't have time, I couldn't add them into the presentation, but I would like to add that by increasing the carbon nanofiber ratio, the mechanical properties like tensile strength and elastic modulus increased. And this is probably caused from the reinforcing effect of carbon nanofibers. And after mechanical tests, we also run some cyclic tests. Applying strain to some level and then turning back to original position, applying strain some level, and we had idea about the cycling behavior of our mechanical cycling behavior of our composites, and then we chose the best ones and used them for electromechanical characterization. So here what we did was, I think in the next one, if you see here, we did the same thing for the films. So we put some electrodes and voltage versus current. This is a 4-prop measurement, and we developed a kind of glue for attaching these copper wires on the sample, and we determined the distance between all these electrodes, and then during the measurement we used a kind of current source, voltage and current source, so we controlled the system and we determined the applied strain. So by using this cyclic movement and monitoring the dynamic change in resistance. So these graphs were obtained by the system that I have told you. And we have used for PVC different levels of strain. So this is 8% and this is 16% for 8 weight percent containing films. As can be seen from here, by increasing the strain level, the change in resistance is higher because we are deforming the material more. And this is the 9% carbon nanofiber containing sample. So, and as can be seen from here, the change from 40s something to 20s and from 70s to 10, but here from 4.5 to around 1. So the change in resistance is lower in this case because at the high filler concentrations, it is really hard to separate the fillers. At lower filler concentrations, we can separate the fillers easier. That means we might have higher sensitivity. So what's happening in our case? So in the first case, the fillers were found like here, and then by applying strain, fillers start to come together. And in fact, when we deform a sample, 2 things happen. Formation of the new bridges and breakdown of the other bridges. So if which one is dominant, it determines the character of the piezo resistance. It can be positive piezo resistance, that means resistance is increasing, or it can be negative piezo resistance, that means resistance is decreasing, system becomes more conductive. So in the first case, at low level of strain, the samples, the fillers, carbon nanofibers come closer, and resistivity decreases, conductivity, resistance decreases, conductance increases. And by increasing the strain level further, then they separated from each other, and since the distance between these fillers increased, and then resistance increased because of the greater interparticle separation. And after making the tests on films, we also checked the fabrics. You see the printed sensor here, and we checked we controlled the percolation behavior on the fabrics, and we got something interesting because for the films that we couldn't get any conductivity or semiconductivity, now we observe some connecting network for the fabrics. This was interesting for us because because at the first case, you know, I thought that did I do anything wrong, and then, you know, when we are talking about plasticizers, you know, it's obvious that the migration tendency is very obvious. So we cut the fabrics around this sensor, and then we extract it in acetone, and then we kind of FTIR analysis was carried out, and then we saw that the peaks were overlapped, and then we concluded that the plasticizer migrated from sample, from connecting layer, printing layer to the fabric during printing or during curing. So, and then we also test.
Hey, Eileen, we're gonna have to wrap up soon just to stay on schedule. I'm so sorry.
Okay, I'm done. And then we have checked the electromechanical properties, and then the morphology, they also worked well. Like, we get even better results than films, because now we had a textile carrier which has a high amount of elastomer in it. And we also checked the effect of filler concentration on sensing behavior, and we concluded that by increasing the filler content, the sensitivity decreased, as I told you before. And also we have analyzed the system before and after the morphology, before and after cycling tests, and we saw that the interface is good. As a conclusion, we have developed a wearable and very cheap sensor. It is a couple of dollars. Thank you very much.